In this video, we're going to talk about differentials, and we're going to start by defining the differential of a function. So let's say that the differential of a function f is going to be written as df, and we calculate it by going f sub x times dx plus f sub y times dy. So I want to just draw a picture here and start to understand geometrically how differentials are useful to us. So let's suppose we're in three-dimensional space and we've got some function f, which we're going to visualize as a surface by saying z equals f of xy. So let's just say our surface looks maybe something like this. And we're looking at 2 points in the xy plane that are quite close to each other. So let's say 1 point's here, 1 point's there. So there will be a tiny difference in the x coordinates. Let's call that little difference dx. And there would be a tiny difference in the y coordinates as well. Let's call that small step between the y values dy. So let's trace both of these points in the xy plane up to the surface. Let's say the first point corresponds to that point on the surface right there. And let's say this point corresponds to maybe that point on the surface right there. So one of the things that we're interested in practice is the difference in the z values between 2 points on the surface. So we could call that difference delta f. So it's the change in the f values or change in the z values as we move between two nearby points. Okay, now the idea is that often this delta f is difficult to calculate. In the context of error, sometimes we have imperfect information, so we're not able to calculate that. But the idea is that delta f is going to be approximately equal to df when dx and dy are small. So the closer that dx and dy are to 0, the better this approximation is. Delta f is closer to df. Delta f in general being the thing that we want to calculate, and df in general being the thing that's easy to calculate in most situations. So let's try a practical example of how differentials could help us. Let's say the point 2, 1 lies on the given curve, and we want to approximate the x-coordinate of the point on the curve with y equal 0.9. So let's just draw a picture here. We've got an implicit function in x and y, so let's just say our function looks something like that. We've got 1 point that we know is on that curve, that's 2, 1, and we're looking at this nearby point. Let's say it's this one, where we know the y-coordinate. We know the y-coordinate is 0.9, and the question we're asking is what is the x-coordinate that goes along with that? So because these are two nearby points on the curve, the x-coordinate would be something close to 2. One way to write this would be to say it's 2 plus dx, because dx is representing a small amount of change, whether that's positive or negative. We'll figure that out as we do the calculation. So this nearby point is 2 plus dx, and we're going to figure out those coordinates. So we're going to start the calculation by letting f represent the left side of the equation of that curve. So the 3x squared plus 3y squared minus 4xy minus 7. And we're going to calculate the differential of this function. So according to our definition above, df is going to be f sub x times dx plus f sub y times dy. Let's calculate that. So f sub x is going to look like 6x minus 4y. Multiply that by dx. And then f sub y is going to look like 6y minus 4x. Multiply that by dy. Okay, so that's our value of df. And now we're going to look at the question and see if we can figure out some values to sub into this to help to our calculation. Okay, so the x and y value we want to work with are the coordinates of the starting point, the point that we were given in the question. So let's say x is 2, y is 1, that's where we're starting from. And then from that point, we're moving over to this new point, 2 plus dx, comma 0.9. So dx is unknown. Finding that is most of the work that we're going to do in the problem. And if we think about dy, well, it's the change that we experience as we go from 1 to 0.9. So it's going to be our new coordinate minus our old coordinate. So 0.9 minus 1, which is negative 0.1. Great. Okay, and then from there we need to think about the value of df. So let's actually start that by thinking about delta f. Okay, so delta f is the change in f values as we move from one point to the other. But remember that the equation of this curve, the way we set this up, we called f the left side of the equation. So in fact, the equation of this curve is just f equals 0. That means this point here satisfies the equation f equals 0, and that point there satisfies the equation f equals 0. So as we move from this point to that point, f is going from 0 to 0, and the actual change in f is 0. Okay, we can say in brackets here, both points satisfy f equals 0, just because they lie on the curve. So any point on the curve has f equals 0, any point not on the curve has f something different to 0. So as we move from one point to the other, change in f is 0. Okay, and then because df is approximately equal to delta f, we can say df is then approximately equal to 0, provided that dx and dy are small. And we're saying in this problem, yeah, these 2 points are close to one another, so we're free to use this approximation. And the smaller the dx and the dy are, the better this approximation is going to be. Okay, so that gives us all the values we need to sub in. So let's sub in and see what happens. So we're subbing into the equation that we have right above the box there. We're saying df is approximately 0. So 0 is approximately equal to, well, we're going to go 6 times 2 minus 4. It's going to be 8. dx is unknown. Plus, we're going to go 6 times 1 minus 4 times 2. So it's negative 2 times a dy value of negative 0.1. Okay, so with a little bit of rearranging here, we can figure out that dx then is going to be approximately equal to negative 0.025. And if we look back at our drawing from the beginning of the problem, we said that the coordinates of this point that we're looking for, the x coordinate, let's just highlight it there, is going to be 2 plus dx. So to finish off the calculation, we're just going to write down 2 plus dx. So 2 plus dx is going to be approximately 1.975. And that gives us the x-coordinate of that nearby point. So that's one of the ways in which differentials can be useful to us. Thanks for watching.